talk about some graphs of functions and some of the basics here. So let's take a look at this graph. Let's assume that this will continue past the window. So I'm going to draw a little arrow right here, one right here. Well, I'm noticing I've got a few things going on. I've got this graph going up to the x-axis and hitting it at 3, 0. It's going to come back down. It's going to reach a point here, 5, negative 1.3 repeating. And then it's going to go up again to 6, 0, hit the x-axis and actually cross it, and then continue going up. So I've got 3 questions. Are the values of the function on the interval the set of x such that negative infinity is less than x less than 3? Are those positive or negative? I'm also going to ask the same question for the interval 3 to 6, and then 6 to infinity. Worth noting here, these are all strictly less than. Okay, let's talk about why that is in a moment. So negative infinity to 3. So if this is negative infinity over here, negative infinity, and I've got positive infinity over here, then from negative infinity to 3, my function is below the x-axis. And that's really what this is asking is this above or below the x-axis? So let me highlight. Here's my x-axis. And if we are below the x-axis, then the values of the function are negative. So here I'm going to say that the values of the function on the interval, negative infinity, less than x, less than 3, these are negative. Okay, because they are below the x-axis. Okay, what about 3 to 6? From 3 to 6, I'm going to travel downward here, and then I'm going to go back, but I'm going to stop right here. So just from here to here, they are also below the x-axis. So this is also going to be negative. What about from 6 to positive infinity? From 6 to positive infinity is way out here, so I just keep going. These are all above the x-axis, so these values are positive. So these are positive because they are all above the x-axis. All right, now let's talk about why this was strictly less than, all these symbols here. Well, we use strictly less than because at 3, so at x equals 3, the y value is 0. So if I were to ask if the entire interval from negative infinity to 3, including 3, are those positive or negative? Well, I would say that most of that is negative, but at 3, we're actually at 0, so which is neither positive nor negative. And then at 6, that same thing happens, where we're hitting the x-axis again, and the point there is at 6, 0. So that's why we've used less than for all of our inequalities in our set notation. But what about increasing and decreasing? Here I've got some kind of complicated definitions. A function is increasing on an interval if f of x1 is less than f of x2 when x1 is less than x2 for any x values x1 and x2. Okay, decreasing is a function is decreasing on an interval if f of x1 is greater than f of x2 when x1 is less than x2 for any values x1 and x2. This is some pretty complicated language. Okay, so in other words, what this is really saying is, if from left to right, and we always go from left to right, if the interval is rising, then it's increasing. However, from left to right, and again, we always go left to right, if the interval is falling, then we are decreasing. So are we going up? Then we're increasing on that interval. Are we going down? Then we are decreasing on that interval. So when I look at this same graph again, and again, let's say this, assume that this continues on past our window. I'll write negative infinity out here again. I'll write positive infinity out here. This is going to ask for the interval x such that negative infinity is less than x, less than 3. So from negative infinity to 3, are we increasing or decreasing? From 3 to 5, are we increasing or decreasing? From 5 to infinity, are we increasing or decreasing? And worth noting here, from negative infinity to 3, we are increasing because we are going up. This entire time from left to right, I am going up. I'm rising. Therefore, this is increasing. Even though all of the values here are below the x-axis and they're negative, that's okay. I'm not asking whether it's positive or negative. Now I'm asking, is it going up or is it going down? So this is increasing, okay, because from left to right, the function is rising. Okay, what about from 3 to 5? From 3 to 5, we are now going down. Which means that we are decreasing on this interval. So here we're decreasing. And this is because from left to right, we always go left to right. Okay, so from left to right, the function is falling. And the last one is from 5 to positive infinity. From 5 to positive infinity. Okay, so here, 5 to infinity, we are increasing. We're going up. So this one is increasing. So hopefully that makes sense. The difference between positive and negative, and then increasing and decreasing. Positive and negative, you're asking whether those values are above or below the x-axis here. So if they're above, then it's positive. If it's below, they're negative. When we're asking about increasing or decreasing, we don't actually care whether it's above or below the x-axis itself. We're just asking from left to right, are the values going up or are they going down? If they are going up from left to right, we are increasing. If they're going down from left to right, then we're decreasing. Which brings us to talking about the average rate of change. Now, you may recall in earlier algebra classes that you talked about lines and slopes of lines a lot. And that was useful because it helped us determine how steep a line was, whether it was, really, really steep and positive, meaning, if you used the kind of terminology of like a person climbing a hill, then it'd be a really steep hill to climb, right? And if it was really steep and negative, then they were sliding down that hill and they were sliding really fast. Your teacher might have used some of these things before. Here, we're talking about average rate of change, which is very similar, except you can use this on functions that are not just lines, and then looking at 2 points on that function, you can determine between those 2 points what the average rate of change is, as if we were to draw a line through those 2 points. What would that slope look like if it were that line? Okay, but remember that this is not going to be used on just a line. This is going to be used on any type of function as long as you've got 2 points. So this is the ratio of the change in the function's values vertically to the change in the x values horizontally. The change in y over the change in x. And my formula here says average rate of change is equal to f of x2 minus f of x1 over x2 minus x1. Now this is some function notation, f of x2 and f of x1, this is just fancy really for saying the y value of your second point. F of x1 is really saying the y value of your first point. So f of x2 is the same as y2, if you will, and f of x1 is the same as y1, if you will. Then x2 and x1 at the bottom here, these are your x values for 0.2 and 0.1 respectively. So let's use this for these two examples. Find the average rate of change for a function with the points 2, 4, and 5, 8. Let's pause there. Anytime you come across a problem with points, take a pause and then label your points. I'm going to, for simplicity's sake, I'm going to label this 0.1 and let's call this 0.2. Well, if this is 0.1 and it has an x value and a y value, then this is going to be x1 right here and this is going to be y1 right here. And if this is 0.2 and it has an x value and a y value, I'm going to call this x2 and this y2. To find the change of rate, or the rate of change, I'm going to do f of x2 and f of x1 are going to go on the bottom. And then instead of, or I'm sorry, f of x2 and f of x1, this is the same as y2 and y1. That's going to go on the top. Okay, so y2 minus y1 over, and then now I'm going to take my x2 and my x1 right here. And that's because y2 and y1, remember I said earlier, this is the same as saying f of x2, and this is the same as saying f of x1. Okay, let's plug in our values. This is 8 minus 4 over 5 minus 2. 8 minus 4 is going to make 4. And 5 minus 2, this is 3. So my average rate of change on this function for these 2 points, this is 4 over 3. Or in other words, if I were to draw a line through those, for every 4 units I'm going up, I would go to the right 3 units. Okay, what about this? Some function with -3, 1, and 4, -12. Again, label your points, x1, y1, and then we'll say x2, y2. We're going to say y2 minus y1 over x2 minus x1. And then plugging things in, -12 minus 1 over 4 minus -3. Now be really careful with your negatives here. If you're subtracting a negative, it's like you're adding a positive. So what I'm going to do is I'm just going to change this like so. All right, this makes -13 over 7. And I'm just going to pop that negative out to the front. -13 over 7 like so. So your average rate of change here is saying for every 13 units, we're going down because it's negative. We're going to the right 7. Just a little bit left to talk about here. Let's talk about some extrema. And I've got zeros on here as well. Well, extrema, this sounds like extreme, right? So these are the extreme highs and lows of your point, or of your graph. And oftentimes these occur at turning points. So when I'm turning from increasing to decreasing, or from decreasing to increasing. When I go from increasing to decreasing, this is going to create a maximum value. Altogether, these are the maxima of the function. These are the high points of the function. When I go from decreasing to increasing, I kind of create a valley, and at the bottom of that valley is going to be a minimum. All of your minimum together, these are the minima. These are the low points of the function. And then I've also got a distinction between local and global. So think about what that means in the world. If you've got something that's global, it's like the biggest of the entire world. right? So here, a global maximum is going to be the highest point, the highest maximum you've got of the graph. If you've got a global minimum, this is going to be the lowest point of the graph. However, if you've got a point that fits this definition, where we went from, say, increasing to decreasing, it created a maximum, but it's not quite the global maximum, then this is a local maximum. And the same thing for a minimum. If it goes from decreasing to increasing, but isn't quite the lowest point on the graph, this is a local minimum. Finally, a zero is a point where you just hit exactly zero. So let's play around with this. I've got a graph here. And what I want to do is I want to identify all of my turning points. Okay, so here I'm going down and I'm turning from decreasing to increasing here. So I'm going to put a point right here. And then I'm going to go up and then I come back down. Let's assume that there's a turning point right here. So I'm going to put a point, then going down and then back up. So I've got a turning point right here. And now this is an interesting one. I'm going up and then it looks as if it's almost got a flat spot here, but then it continues going up again. Now, because I didn't go down, because I didn't go from increasing to then decreasing, this isn't going to be one of my extrema. So I've just got these three. We'll assume that this graph will just continue going up and up. Let's label what these are. This top one here, I'm going from increasing to decreasing. So at the top of all of your hills, as you're going from increasing to decreasing, this is going to create a maximum. And then these two, when you go from decreasing to then increasing, so you're going down and then now you're bouncing and you're going up, this is going to create a minimum. Now, I haven't labeled whether these are global maximums, global minimums, local maximums, local minimums. Let's do that now. This point here is a maximum. However, it is not the highest point on the graph. Right here, we're just going to keep going up this way. We're going to keep going up this way. So this is not a global maximum. We'll call this just a local. This is a local maximum. Right here, same thing is happening. I'm going from decreasing to increasing, so I've created a minimum, but it's not the lowest point on the graph. So this is a local minimum. However, this point, this is a minimum going from decreasing to increasing, and it is the lowest point on the entire graph. Therefore, this is the global minimum. We actually don't have a global maximum. And that's because in order to have a minimum or a maximum, it's got to be a defined point. We've got to be able to look at it. We've got to be able to say this exact point is the global maximum. It's the highest point on the entire graph. Well, if I were to define a point on this graph, I could just find another point that's higher because this will continue to go up and up and up and up. So because of that, there is no global maximum. What about zeros? This is where f of x, or the y value, is equal to 0. It is exactly 0. Or in other words, graphically, that's when you hit the x-axis. When your graph hits the x-axis, the y value is 0. That's why these are called zeros. So hopefully that helps define a little bit more of what you're looking at when you do look at graphs. You know, what is positive, what is negative, what is increasing, what is decreasing, how to find the average rate of change, as well as what points are your maximums, your minimums, and your zeros.